Thinking at this point of actually going back to here, and I meant to go through this point by point in the first example, and I just completely forgot. So just check, have we been doing this? At the beginning, we've always defined the null and alternative hypothesis, decide on a significance level in real life, in the exam questions, and in the book you're basically told what that is. Calculate the critical value, and that gives you the critical region. Calculate the test statistic. Well, that is normally given to you in the questions we've had so far, although you could be given a set of sample values and had to work it out yourself. Decide on the outcome of the test, depending on whether or not the test statistics values in the critical region. State the conclusion in words. Okay, that's what we should be doing. So, fourth example, if we find that one, example number 4. It takes on average 21.75 seconds for a lab rat to complete a task. Placed in a different environment, a random sample of 50 times taken to complete the task was recorded. Now these should be sigmas. The font's changed, okay? Those should be uppercase sigmas there. So, doing it 50 times, we have some data. Sigma t, total time, and the total square times. Test at the 5% level whether the new environment has changed the mean time to complete the task. So, let's start off. H0. We have to test at the 5% whether the mean has changed. H0 will be it hasn't changed. So it will be mu equals we're not told what mu is. Exactly. So what shall we do? Sorry? What is the sum of t over 50? What are you working out there? And why are you doing that? Because the sample mean is also the unbiased estimator of. Yeah, we do not know that, so we have to use the unbiased estimator of it, which is x bar, or t bar in this case we're using t, so that is sigma t over n 1107 over 50, which is sorry?
Why is the slot meter not the 21.75?
Oh, you're quite right. It's 21.75.
This would be for
I
the
haven't read the
X
question. Yeah, you're quite right. That's a load of rubbish. Scrub that out. Sorry, thank you. Well plotted, okay? If you actually read the question carefully, it tells you that this is the great god of statistics who I have not been listening to today. The great god of statistics tells us that actually it's 21.75. Thank you. Well spotted, Mr. Jones. Well spotted. Okay, there we go. Thank you. The alternative hypothesis, it says here, has it changed? So that's a not equal to 21.75. That's a two-tail test. And we are doing this at the 5% significance level. So, diagram to start with. Assuming H0 is true, we are dealing with T. Mean 21.75. Two-tail 5%. What's going to be the area at each of these endpoints? 2.5%. Yep. 2.5% there. 2.5% there. That gives us our 5% altogether. So we're going to be interested in two critical values, call them C1 and C2. Distribution T bar rather. So we need the distribution of T bar. T bar is always normal mu sigma squared over n. I was jumping the gun earlier. Mu is given to us in the question. We are assuming that mu for the null hypothesis is 21.75. It's sigma squared we haven't got. So for sigma squared, we have to use sigma squared hat. Can anybody remember how do we work out sigma squared hat?
N over minus 1 S squared.
That's correct, where S squared equals the sample variance. And in terms of what it gave us in the question,
sigma t squared over n minus mu squared, or sigma t over n mu squared.
yeah, Okay, that's right. So
Why would you use? Why would you not use the 25.75?
in this,
Because that's the mu. Oh, actually.
that's a valid question,
They
and
are different values.
they are different values. Yeah,
Who knows?
I haven't got a perfectly ideal answer for you on that one. Okay, but we're using our sample here. We use a sample for the whole thing. Okay, so we should have here that big 24,000 number divided by our sample size minus the other number over that squared, or s squared. Does anybody have an s squared number? Yeah, that's what I've got. Okay. So now I need to work out my sigma squared hat, which is n over n minus 1 s squared. Has anybody got a sigma squared hat value? 1.701 is what I've got here. So T bar will be distributed, we said over here, normally, mu, which they told us, and over here, sigma squared hat over n. So that's the distribution of T bar. It is a common mistake sometimes that because people have already used the n and the n minus 1 thing here, some people forget to use the n down here, but it still has got to be there. Well, I say some people forget to do that, I think I'm probably talking about me. Okay, so we've got a distribution of T bar. We need to find, well, let's have a look. What is our sample mean? Have we actually worked out our sample mean? We haven't, have we yet, properly? So our sample mean, T bar, which was 1107 over 50, 22.14. I'm just going to slide that up to look at the diagram, okay? So that's to the right of our mean. So we're going to be interested in the C2, the critical value on the right. So what we are interested in then is finding C2 such that the probability that T bar is greater than C2 is 2.5%. So we'll turn that round into a less than, and 1 minus 2.5% is 0.975. I can phi this bit, it's my value, take away my mean, over my standard deviation, and anti-phi 0.975 from the tables, 1.96. Again, that one you will also memorize. Sorry, I've anti-phied too early here. Sorry. 0.975. Do we have a value for C2 anywhere? 22.11. Our sample mean was 22.14, so that was over there. So, our sample mean is in one of the tails. If it's in the tail, that means that we yes, H0 is incorrect. So if it's in the tail, we reject H0, which means we now have no option other than accepting H1, and that was mu is not 2NT1.75. In other words, the mean has changed. So the environment, the different environment the lab rats were put in, has made them slower.